In this video, we will learn the questions from second chapter of NCERT textbook for grade 12. The chapter is electric potential and capacitance. Total questions in this chapter you would be finding 1 to 11. We will see all of them one by one. So first question is saying that there are two charged particles 5 into 10 raised to minus 8 coulomb and minus 3 into 10 raised to minus 8 coulomb are located 16 centimeter apart. At what points on the line joining the two charges is the electric potential 0? We can first consider that there will be a point P between these two charged particles on line joining them, where we can assume that potential would be 0. This is point P, which is a distance r from A and 16 minus r centimeter from B. The formula for the potential, already we have been through many questions in the previous videos. 1 by 4 pi epsilon naught qa upon r is equal to 1 by 4 pi epsilon naught qb upon the distance from B, that is 16 minus r. 1 by 4 pi epsilon naught will get cancelled and it is qa 3 into 10 raised to minus 8 upon r is equal to qb 5 into 10 raised to minus 8 upon r. Again 10 raised to minus 8 would get cancelled and it will be 3 upon r is equal to 5 upon 16 minus r. After getting cross multiplied, it is 5r is equal to 48 minus 3r and 8r is equal to 48, and hence r is equal to 6 centimeter. So from A it is 6 centimeter, but from B it is 10 centimeter because total distance is 16 centimeter. Now the question is points. Can we take only point P where potential will be 0? Or any other point is there where potential is 0? So there are other points. That point we have to consider either near to B but outside the line joining, or near A outside the line joining, on the line joining. So near A, if you are going to consider, it is quite comprehensive because A is having small magnitude in comparison to that of B. If the point we are going to consider near B, B would be having already higher potential that may not be computed by A, that may not be encountered by A, that may not be equal in magnitude or in opposite sense which is produced by A, and we would never be able to get 0 potential near B. So we are going to consider now the next point near A but outside these two charges on line joining. So this distance again we are considering r from A, and the distance from B obviously would be going to be 16 plus r. Same formula, same equation, only the 16 minus r would get changed as 16 plus r, and after simplifying you will be getting r is equal to 24 centimeter from A or 24 plus 16 centimeter from B. So there are 2 points where potential would be 0. In between we are getting, because one is positive, another one is negative, the potential of positive and the potential of negative would be same in magnitude but opposite in nature. That is why it has to be 0. Question number 2 is saying that there is a regular hexagon of side 10 centimeter has a charge 5 microcoulomb at each of its vertices. Calculate the potential at the center of the hexagon. This is the regular hexagon, and on each vertices there is a charge kept 5 microcoulomb. If you know that the distance from the center to any of the vertices of the regular hexagon is nothing but equal to its side, because we can take 6 equilateral triangle having each equal in side, and then we are going to arrange in the way you can see the diagram, it would form a regular hexagon. So side if 10 centimeter is given, it means from center to any of the vertices the distance will be 10 centimeter. So what we can do, we can calculate the potential because of one charge, that is 1 by 4 pi epsilon naught q upon r or kq upon r, and then we can again find for the second one, again for the third one, and add all of them together. That will be kq upon r. How many times we have to add? 6 times. Or we can directly multiply 6 into kq upon r. You put all the values, 6 into 9 into 10 raised to 9, 5 microcoulomb upon 10 centimeter you have to change into meter, and then the voltage would be coming as the final answer. Now question number 2.3 is saying two charges 2 microcoulomb and minus 2 microcoulomb are placed at points A and B 6 centimeter apart. If you see the question, they are appearing as the virtual dipole. The one is plus 2, another one is minus 2, and distance is 6 centimeter. Question is identify an equipotential surface of the system. Now what is equipotential surface? So equipotential surface is a surface in electric field. At every point on this particular surface, the potential remains unchanged or potential remains same. And we have done in theory part that potential would be same on a surface is obtained always perpendicular to the electric field. So first of all, let us try to have the electric field lines for this particular dipole or for the system of two charges having plus 2 and minus 2. So electric field lines, you know already, it is originating from positive charge and terminating on negative charge. So it would terminate from positive and it would originate from positive and going to terminate on negative charge. And on this line, if you really see, the red line which is showing the equipotential surface, wherever we are going to draw, it is appearing as perpendicular to the electric field. Between these two equal and opposite charges, it would be straight line, not straight line, straight plane at which potential would be same, and after that the plane would be making a convergence towards the charges, because the field lines are going to originate, going to converge or going to diverge from a particular point. So this is going to make the converging spherical, a part of sphere like that shape or surface it is going to form. So this will be the red line you can see is nothing but the equipotential surface for the system. And the question is, what is the direction of the electric field at every point on its surface? Already we have discussed, it is perpendicular to the electric field. Question number 4, a special conductor of radius 12 centimeter has a charge 1.6 into 10 raised to minus 7 coulomb distributed uniformly on its surface. What is the electric field inside the sphere? Inside the sphere, electric field is always 0. It's the concept of electrostatic shielding as well. That shielding we will be try to describe in coming videos. But shielding means if we want to keep any electronic devices away from any electric influence, we can keep inside a charged shell where inside electric field will be 0. Example, suppose you are traveling in a car and there's a thunderstorm situation over there, and because of the lightning you want to protect yourself, so better to be inside the car. Don't come out, don't go near under a tree or near electric pole or any other material present outside. So it's better to be inside, because during thunderstorm, during the rain, when even if the lightning is going to strike your car, inside electric field will be 0. With the help of the flowing water or any other earthing, the high amount of potential or that lightning potential would be earthed or going to the ground, so you would be saved. That is the example of electrostatic shielding we can take. So here inside electric field will be always 0. Just outside it is equal to kq upon r square. So you can put the value 9 into 10 raised to 9, q 1.6 into 10 raised to minus 7, and upon r square 6 centimeter. So we'll change into 12 centimeter, we change into meter and then square. After calculation, this will be the final answer. In C part, it is saying at a distance 18 centimeter from the center of the sphere. Now r you have to take same formula, but you have to take r as 18 centimeter. So 18 centimeter again square. After calculation, this will be the final answer. Question number 2.5, there is a parallel plate capacitor, air is placed in between, and the capacity of this parallel plate capacitor is 8 picofarad. 1 pico is 10 raised to minus 12. And what will be the capacitance if the distance between the plates is reduced by half and the space between them is filled with a substance of dielectric constant 6? The formula for the parallel plate capacitor is epsilon naught A upon D, that D is the distance between the plates, A is the area of each plate, epsilon naught is the medium in which the plates are placed. So here, as per the condition given in the question, the distance should be reduced to half, and in between the plates we should put some dielectric material having dielectric constant 6. So once we put this dielectric material, the new capacitance would be epsilon naught into epsilon r A upon d dash. You put the value of d dash as well, and epsilon r 6, it will be 12 epsilon naught A upon d. It means it is going to be 12 times to its initial value of capacitance, and initial value of capacitance is nothing but 8 picofarad. If we multiply, it will be 96 picofarad. It is increasing by 12 times. Question number 6, 3 capacitor, each of capacitance 9 picofarad and are connected in series. Just before going to question number 2.6 and question number 2.7, I just want to have a brief explanation of series combination and parallel combination, because it's important to you for you to know that how and why easily we can find the answer of series combination as well as parallel combination. So combination, there are two types, series combination as well as parallel combination. These are the combination. But while finding the equivalent capacitors, we need to assure ourselves that we can first recognize the combination, second we can apply the appropriate formula over there. If you have been through the chapters which we are going to have in 12th standard, if we exclude 11th standard, we have total 4 combinations. Out of 4, 2, 3 we can learn in first 2, 3 chapters, like first chapter, this second chapter, this combination of capacitor, then combination of cell, then combination of resistor, and in electromagnetic induction, combination of inductors. That combination of inductors nowadays it is not there in syllabus, it has been deleted. But these 3, this year also I guess that resistance combination is not there in 2023-24 session I am talking about. But this capacity it does existence in the syllabus. So first let us learn how the trick we need to apply for any combination, whether it is of resistance or for capacitance. Here we are going to emphasize on capacitance. The basic formula is Q is equal to CV. If I ask out of these 3 which one is constant, you will say C is constant. It means if Q is going to change, V will be changing. There are 2 combinations, parallel and series. If in either of the combinations we fixed any of them like Q or V, the other one would be fixed into the, like suppose parallel combination I am going to fix Q, then V would be fixed in series combination. Or in parallel combination I am going to fix V, Q would be distributed. In series combination if I am going to fix Q, V would be distributed. For example, look at this P, this is the trick mnemonics we are going to keep in mind, and P, the parallel word starts with P, potential word starts with P, and positive word starts with P. This you need to keep in mind, because in parallel combination potential across each, when I say each, it may be each capacitor, it may each resistance, it may each cell, or so on and so forth, must be same or would be same. I repeat, in parallel combination potential across each capacitor would be same. It means in parallel combination charge on each capacitor would be different. Similarly, take this into the series combination. Series there is no mnemonic, but whatever is left untouched in parallel would go in the series. Like in series combination, charge remains same on each. You got this point? So, and this last word is positive. It means in parallel combination all positive will be connected together to the positive terminal, and next line, you know, all negative would be connected together to the negative terminal. But in series combination we don't do so. We do positive, negative, positive, negative, positive, negative. Like you put cells in the torch, positive, negative, positive, negative, positive, negative. So here if we see in a parallel combination, because charge is getting distributed in the mnemonic, you can see parallel, potential, positive. You always keep this in mind whenever you go across any combination. In parallel combination, potential remains the same. That's it. Positive means all positive, all terminals together to positive, all terminals together to negative. And if something is left, like take V is equal to IR, R is constant, V is potential, I is current. So there you can say in series combination current is same, because in parallel combination potential is constant. Constant means equal to applied. If we have applied 220 volt, take the example of your household wiring. If you have the fan or the tube lights or the LEDs or the television, any music player, ACs, these all appliances are running on 220 volt supply, and we are getting how much? 220 volt in a household from the mains. So this is parallel combination. All the apparatus which are installed in your household, it is in parallel combination. Series combination, you can take the example when we take the different that glittering lights, the series of lights, small bulbs or LEDs which we connect to 220 volt. They are in series. 40 volt each is having suppose 6 volt or 5 volt, it will be 40 into 5, 200 volt, and we can connect them to the main supply of 200 or 220. Alone we cannot, because in series combination potential or the voltage gets divided. So here if you see the parallel combination, here is the parallel combination, it is charge is conserved. So total charge is equal to Q1 plus Q2 plus Q3, and the formula is there, Q is equal to CV. So for equivalent, if we are going to write, I am taking in short only, equivalent we are going to write, that will be Q is equal to C equivalent V, Q1 is equal to C1B, so on and so forth, and then C equivalent is equal to C1 plus C2 plus C3. It is added in parallel combination. So whenever we are going to add the capacitance in parallel combination, the equivalent capacity is going to increase. It means the equivalent will be larger than the largest individual. If 2, 3, 5 we are going to add, it will be 2, 3, 5 plus 5, 10. So 10 is much bigger than the larger individual, that is 5. Now in series combination, energy is conserved. We can take the formula, V is equal to Q upon C, and then Q, because in series everywhere it is same on each capacitor, it will be taken common and cancelled, it will be 1 by C cube. So reciprocal. Reciprocal means it will be smaller than the smallest individual. If 1 and 2 is getting added, the equivalent will be even lesser than 1. So formula you can choose parallel, algebraic sum, series, reciprocal, 1 by C equivalent is equal to 1 by C1 plus 1 by C2. Now let's look at this question number 6. 3 capacitors, each of capacitance 9 picofarad, are connected in series. Connected in series, 9 picofarad. Look here. The question is, what is the total capacitance of the combination? Can we first find the total capacitance? Apply the formula which we have obtained. It is 3 picofarad. Now B part is, what is the potential difference across each capacitor if the combination is connected to 120 volt supply? So if the connection is connected to 120 volt supply, what is the potential difference? From the definition itself, potential is constant in parallel. Potential would get divided in series. So series, because all the capacitors are equal in capacity, 9 pico, 9 pico, 9 pico, the the voltage would get divided equally. So 40 volt, 40 volt, 40 volt. Now question number 7 is saying that 3 capacitors are connected in parallel, 2, 3, 4. What is the total capacitance of the combination? 3 capacitors are connected in parallel having value 2, 3, 4. The voltage supply is 100 volt. Question is, what is the equivalent capacitor? You know the formula, algebraic sum, if you add it is 9 picofarad. Determine the charge on each capacitor if the combination is connected to 100 volt supply. What is the formula of charge? Q is equal to CV. So Q1 is equal to C1B, and you know in parallel combination potential remains the same, but charge is not. So for each capacitor we are going to take 100 volt, 100 volt, 100 volt. Unlike series we took divided, Here we are not supposed to take that. It will be constant and it will be equal to applied. So C1, Q1 is equal to C1V, then C1 200 volt, pico 10 raised to minus 12, it will be 2 into 10 raised to minus 10 coulomb after multiplication. Similarly Q2 3 into 10 raised to minus 10, and Q3 it will be 4 into 10 raised to minus 10 coulomb. Question number 2.8, in the parallel plate capacitor with air in between plates, each plate has an area is given 6 into 10 raised to minus 3. Then distance between the plates, that D is given 3 mm. Calculate the capacitance of the capacitor. We have to find the capacitance of the capacitor. Next part is, if the capacitor is connected to 100 volt supply, what is the charge on each? The question is quite simple. First let us calculate capacity. C is equal to epsilon naught A upon D, and put the value of epsilon naught, then A area, then D distance, and then it will be coming as 17.7 picofarad or 17.7 into 10 raised to minus 12 farad. The question is how much charge is going to appear on it. So formula for charge, Q is equal to CV, and the voltage is given 100 volt. You multiply by 100, it will be 17.7 into 10 raised to minus 12 into 100 volt coulomb, 100 coulomb, it will be 1.77 nano coulomb, maybe positive, maybe. Oh, now the question is, what is the charge on each plate? Yeah, one plate is positive, another plate is negative. So first plate, which is connected to positive plate, would get positive charge, similar amount of charge, but negative would be attained on the second plate. In this question, it is saying explain what would happen in the capacitor given in previous question if a 3 mm thick mica sheet of dielectric 6 were inserted. First condition is while the voltage supply remains connected. See, in the previous question already we have obtained two things. First, the capacity at 17.7 picofarad, and the charge coming on the capacitor when it is connected to 100 volt supply, that is 1.77 nanocoulomb. The first one positive, another one is negative. Here the question is saying that there is a dielectric material is being put between the plates. 3 mm thick, distance was also 3 mm, so it means it is fully inserted inside the parallel plate capacitor. So what is the new capacity? So C is 17.7 picofarad. New capacity formula would be C dash is equal to epsilon naught epsilon R A upon D, or K epsilon naught A upon D. If we put all the values, already we have 17.7, so better multiply by 6, and then it will be 106.2 picofarad. Now this is the new capacity. If voltage remains connected, which we are going to take in condition A given in the question, Q, the charge would be increasing because capacity is increasing. Now it is able to hold or accumulate more or more charges. So when capacity is going to increase, charge would be increasing, charge would be accumulated on the plates because voltage remains connected. So new charge will be C dash V. C dash is 106 picofarad and 100 volt. After multiplying, it will be 1.06 into 10 raised to minus 8 coulomb. Part B, after the supply was disconnected, this mica sheet is being inserted. So before the mica sheet is being inserted, what was the charge? 1.77 nanocoulomb. But the voltage was 100. Now the capacity is going to increase, so potential difference between the plates will be different, and that will be Q upon C dash, that is 1.77 upon 106 pico, means 10 raised to minus 12 farad, and after simplifying it we will be getting 16.7. In this question, 12 picofarad capacitor is connected to a 50 volt supply. How much electrostatic energy is stored in the capacitor? If you see the formula of energy stored in capacitor, it is nothing but half CV square if C and V both are given, then half QB if charge and voltage both are given, or half Q square C if charge and capacity both are given. But here in this question, C and V both are provided. We have to apply half CV square. We will be putting the value as half C 12 pico 10 raised to minus 12, voltage square as 50 into 50, and after calculation we will be getting 1.5 into 10 raised to minus 8 joule. Question number 11 is there, is saying that a 600 picofarad capacitor is charged by 200 volt supply and then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor. How much electrostatic energy is lost in the process? First of all, we know that charge is transferable. Charge can be transferred from one point or one body, one conducting body to another body. In this process, some energy does loss actually, but where that energy goes? Question is that, because energy is conserved, neither be created nor be lost. So if you have observed that while charging your mobile phone or charging your battery, it gets heated, sometimes sparks also appear. So in heating or sparking, whatever the energy is going to be lost, that energy we cannot actually revive. It goes to environment as heat energy. That environment is the big sink we know for the heat energy. So, but here we do have to calculate the total loss in energy in this process because charge is being shared here. So before going to this question again, I just would like to explain the sharing of charge, what actually happens over there. So when two charged particles, suppose one is having charge Q1, obviously capacity is C1, voltage is V1, so C1 V1, and another one is having charge Q2, having capacity C2, voltage V2, so it is C2 V2. Now what we are going to do, we are going to connect them. What will happen? Charge will go from high potential to low potential. In this particular diagram, we don't know which one is kept at high potential, which one is kept at low potential, but it will go from high potential to low potential. Now, the process will get continued until the potential of both becomes the same. The moment potential of both becomes same, the situation is called the equilibrium with respect to charge, and the potential at that point of time is called common potential. So what is the formula for common potential if you want to calculate? We need to know total charge after combination. Before combination we know Q1 is equal to C1 V1, Q2 is equal to C2 V2. After combination it is addition of both Q1 plus Q2 because charge is conserved, charge is constant, neither be created nor be lost. Total capacity is nothing but capacity, algebraic sum of capacity, individual capacities, that is C1 plus C2. Now we have Q is equal to CV, V is equal to Q upon C. Q means total charge Q1 plus Q2, C means total capacity C1 plus C2 when we talk about common potential. And we know that common potential Q1 plus Q2 is C1 V1 plus C2 V2, and then C1 plus C2 is the total capacity, so it will be Q1 C1 V1 plus C2 V2 upon C1 plus C2. This is the common potential. Now we know the energy formula is half CV square. So if you talk about energy of first and energy of second before sharing of charge or before they have been connected, it is half C1 V1 square plus half C2 V2 square. And if we talk about before sharing total energy, it will be half C1 V1 square plus half C2 V2 square. After sharing, what will happen? Half C1 plus C2 total capacity into V, that V is common potential, V common square. So if we put the value of V, that is C1 V1 plus C2 V2, it will be half C1 V1 plus C2 V2 upon C1 plus C2 the whole square. Now you have the total energy before sharing, you have the total energy after sharing. Let's find the difference. After minus before or before minus after. If after minus before or before minus after is coming to 0, it means during sharing no energy is being lost because energy is conserved. And if after minus before is coming negative, it means does loss of energy occur in the process. If it is coming positive, it means energy is being gained in the process. So now let's have some mathematical aqua here. We are going to find delta E as E sharing after minus E before, and be very careful about the calculation, it is going to be little tough. Half C1 plus C2 and then C1 V1 plus C2 V2 the whole square upon C1 plus C2. Simplify it. We are going to take square term individually. From here C1 plus C2 would get cancelled by the square term, and then the remaining part, if we see C1 V1 plus C2 V2 we have the formula a plus b the whole square. And what is the formula a plus b the whole square? For this particular part I am talking about, a square, for this particular part, a square plus b square plus 2ab. So if we expand this on that particular formula, it is c1 square v1 square plus c2 square v2 square plus 2c1 v1 c2 v2. Remaining next part, c1 plus c2 you multiply to the c1 v1 square plus c2 v2 square. It will be c1 square plus v1 square plus c2 square v2 square plus c1 c2 v1 square c1 c2 v2 square. Negative you multiply inside. The term which are positive will get negative, and then two equal and opposite with positive and negative sign will get cancelled. Look carefully here. This also will get cancelled here. And now we are left with this 2c1 v1 c2 v2, c1 c2 v1 square, c1 c2 v2 square. What we are going to do, 2c1 c2 we will be keeping common. c1 c2 you keep common, and it will be v1 square minus v2 square plus 2v1 v2. Now again minus sign we are going to keep common. It will be v1 square plus v2 square minus 2v1 v2, and it is nothing but a minus b the whole square. So it will be v1 minus v2 the whole square. You can even write in modulus v1 minus v2 the whole square. So this formula is coming negative, and we have obtained after minus before. After minus before coming negative, it means after it is small, before it is bigger. Then only the substitution will be, subtraction will be negative. So it means the charge, after sharing of charge, the energy loss occurs over there. Loss in energy occurs. So how much formula we are going to use for the previous question? It is delta E is equal to minus C1 C2 upon 2C1 plus C2 into V1 minus V2 the whole square, or modulus of potential difference the whole square. Now come to the question again. First C1 is given 600 picofarad, V1 is 200 volt. For C2, the one which was uncharged, voltage will be 0, and similar capacity means 600 picofarad. Apply the formula. It is 600 into 600 pico upon 2 into 600 plus 600 into 200 minus 0 whole square. 600 if you multiply, it will be 36, 4 times 0, and p into p means pico, and then upon this 1200 into 2, 2400 pico. Cancel some p to p, then 0 to 0, and after calculation it will be 364 times 0 upon 24 into 400. Again simplify it, it will be 40 would be making 10 raised to minus 12 as 10 raised to minus 6, and it is 6 into 10 raised to minus 6, because 6 4s are 24, and then 6 6 are 36. So it will be 6 into 10 raised to minus 6 joule loss in energy. We have not taken here negative sign because in the question it is already asked how much loss in energy occurs. So 6 into 10 raised to minus 6. Now you must be thinking, is this the only process to solve the question? Can we apply some other process? Obviously we can. That is the simple method where you can take C1 as this, C2 as this, and before the connection you find the, or first capacitor, what is the total energy, you find E1 is equal to half C1 V square, and it would be coming as 12 into 10 raised to minus 6 joule. And then next time, because you are going to connect them in series, connect 1 by C dash is equal to 1 by C plus 1 by C. So after combination the equivalent capacitor will be 300 picofarad, and then voltage remains the same. The previous voltage, how much? 200. So find the E2 now. What is E2 now after calculation? Half C dash V square. It is coming as 6 into 10 raised to minus 6 joule. So earlier the energy was 12 into 10 raised to minus 6 joule. Now it is 6 into 10 raised to minus 6 joule. How much lost in energy occur over here? So E1 minus E2, 12 minus 6, and it is nothing but 6 into 10 raised to minus 6 joule. So this is the another way for this particular question, because we must know, but the previous one you can solve by the sharing of charge, and how much loss in energy occurs, you can see the final formula in the sharing of charge. Thanks for watching.